Hi everyone, I'm Adam. In this problem, for our given surface generated by the rectangular equation y equals x squared, we're going to find the equivalent equation in cylindrical coordinates. So to start, what we want, we have a rectangular equation, and so naturally what we want is an equation going from, say, x's, y's, and z's to cylindrical coordinates, where we have r's, thetas, and z's. And so naturally, when we write the equation in cylindrical coordinates, we don't have to have all of r, theta, and z. As we notice, we just have y equals x squared. There's no z present, but it's still an equation in rectangular form. But we just want to transfer everything into whatever we can get on this side if we can. So how are we going to do that? So we're going to start by looking at our conversion equations. So we have y equals x squared, and kind of thumbing through our list, we know that just starting on the left-hand side, y can be written as, say, r sine of theta. So that gives something on the left. And we have x squared, and we know that x can be written as r, say, cosine theta. And we also have r squared is equal to y squared plus x squared, but I think we have enough to go on right here. So we're going to make these two substitutions into our rectangular equation. So y, the left-hand side, is going to be equal to r sine theta. Well, let's just go ahead and maybe bring the equation down here. Okay. So our left-hand side, y, is r sine theta, and that's equal to x squared, but x is r cosine theta. So squaring x means we square the r cosine theta, giving us r squared cosine squared theta. Okay, now technically we're done. We have an equation in terms of r's and thetas, again no z's, but that's all right. But convention says we want to clean this up a little bit, and so what we're going to do is we're just going to solve this for r. Okay? So in looking at this, we have an r on the left and an r squared on the right. So we have one too many factors of r to solve it for r explicitly. So we're going to just do a little bit of algebra. Noticing since we have a factor of r on both sides, we can, say, divide through by r. So our r's will cancel on the left, and our r will cancel with one of the r's on the right. So we'll have sine theta is equal to r times cosine squared theta. So we'll rewrite this. I'm just going to flip-flop the sides. Since we can solve for r, we'll try to put the r on the left-hand side. So this equation again is r cosine theta, cosine squared theta, is equal to sine of theta. Okay, we want to solve for r, so dividing both sides, say, by cosine squared, that gives us r is equal to sine theta divided by cosine squared theta. Now, like I said, we want to solve it for r. Again, we could say we're done, but we'll just clean this up a little bit more. So sine divided by cosine squared theta, we can have r is equal to, you can write this, factor the bottom a little bit, and maybe write this as r is equal to 1 over cosine theta times, say, sine theta over cosine theta. And so what does that give us? Well, that's going to give us that r is equal to 1 over cosine, that secant theta times sine over cosine is tangent theta. Okay, so there's our equation in cylindrical coordinates. Okay. Now, there's one little technicality we have to pay attention to. So when we did our algebra over here, going back to the beginning, when we divided through by r, that's okay to do for any value of r, except we can't divide by 0. So when we made that algebraic step, we're kind of supposing that r is no longer 0. So technically, from everything that preceded, subsequently, if you graph that, you're going to be missing the point wherever r is equal to 0. But now if we look at the end product, we have a value for r equal to 0. Namely, for any multiple of pi, tangent of theta is equal to 0. secant of theta is defined there, so r would be equal to 0 there. So we haven't really lost any points in our graph. So if you graph the surface generated by this equation, you will get the original surface from y equals x squared. Thank you very much.